The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome to Leakage Current Testing 102 webinar. This is a continuation of webinar from our previous Leakage Current 101. Before we get started, I'd like to introduce myself. I'm Bisham Patel. I'm an application engineer here at Iconics USA, which covers associated research brand. And then I have Syed Abidi, who will be the panelist for this webinar, and also Amanda. Amanda is going to be doing the organizing for the webinar. A few notes before we get started. There's a question and answer utility. Please use this utility to kind of ask questions about the webinar, and Syed will be answering this live as I present this material. If you have any audio or visual difficulties, please use the chat box to ask questions to Amanda, and Amanda will respond with some troubleshooting steps for you. If you need a copy of this presentation, you could always email Amanda. Her email address is listed here, amanda.booth@iconicsusa.com. If you ever need a copy of the actual webinar, the presentation, the webinar is also recorded, so we'll provide a link to the recorded webinars on our website. For today's webinar, we want to go into details of touch current testing or leakage current testing. I want to define what types of touch currents there are. We'll take a look at touch current test, patient leakage test, patient auxiliary leakage, and some of the more advanced test types that are required called mains on applied part or mains on SIP-SOP. We'll start with some definition of leakage current. We'll take a look at what kind of network is needed, what kind of measuring device is needed, what kind of stipulations the standards puts on to run this leakage current test. We'll also take a look at the standards, a brief standards review, or look at some of the images in the standards and how that relates to running a leakage current test. Specifically the 60601-1 third edition. Most of the images that we used comes out of the 60601 standards, and I'll also review some of the information provided in those images. And we'll take a look at some of the app notes that we have created to kind of make it easy for our customer to perform the mains on applied part test or any kind of leakage current test that you may have to comply to. So these are our learning objectives for today. First, we want to start with the types of leakage current. What type of leakage currents you could have. Now, a definition of leakage current or electric current through a human body when it touches one or more accessible part of an installation of surface or electrical equipment. This definition comes out of the standard 60990 second edition, and this is where a majority of your touch current requirements comes from the standards. This is also called an enclosure leakage current. Now, a leakage current that happens on the surface of a product, basically this definition is describing what kind of leakage current you could observe or feel or measure if a product is powered on, and any excessive leakage current flowing to the chassis. When we go into patient leakage current, another type of current is called patient leakage. If you have types of applied part, now we go into medical field, products that are going to be coming in contact with direct contact with the patient. Current flowing from a patient connection via patient to earth. So imagine you're hooked up to a pulse oximeter. What kind of leakage current can you feel at that point? So we get into the medical field, the patient leakage current are really important. Another current might be current originating from an unintended appearance of voltage from an external source on patient following a patient wire to connection of a F-type applied part. So when we get into the definition of applied parts, we'll take a look at how the requirements have additional testing requirements to do what we call mains on applied part testing. So the second definition here lists out how to perform or the definition of what would happen in the mains on applied part testing. Another type of leakage current test is also known as patient auxiliary current. This is the current that flows between applied parts. If you have two different types of applied part, is there any leakage that flows between these products or between these points? It could be from an applied part to an applied part leakage current test. Not only that the current could leak to ground, but it could leak between the 2 points. And then mains on applied part. Again, like I mentioned earlier, this is an application of mains voltage applied through a human body or human body network directly onto an applied part, and to measure any resulting leakage current that may happen due to the external application of voltage. Now, again, these definitions, or some of these definitions, come straight out of the standard. It's kind of important to understand what the standards is trying to achieve and what test types they are trying to ask you to perform on your product. For leakage current 102, we want to specifically concentrate on medical field where there's patient leads, and patient leads are defined in two types of parts, applied parts. So you could have a F-type applied part or a B-type applied part. Now, the B-type applied parts are basic insulation that provides isolation from earth. Imagine a hospital bed. It comes in contact with a human being, but it does not have any medical contact with the human being. So in this case, having an earth or grounded medical bed is considered a B-type applied part. You're coming in contact with the patient, but this is a non-electrical contact, and you're grounding the bed is enough to kind of allow you to run some B-type applied part testing. For an F-type applied part, you're required to have additional isolation between any type of internal of the medical equipment. And an F-type applied part requires you to have additional isolation from the mains input for your product. And a subtype of F-type products would be considered as a BF type. Again, this is a floating, the F-type applied part providing higher degree of protection than a normal B-type product. So BF types are additional isolation compared to your B-type products. And then when you get to CF type applied part, in a CF type applied part, you're looking at type of products or applied parts that are in direct contact with the cardiovascular system of your body. So anything that comes into direct contact with the neurological neurons of your body or nervous system of your body, you're creating a direct contact for the electrons to move around in your body. So these are the more stringent parts. They come in direct contact with inside of your body, could easily cause additional shock hazards. And the requirements for a CF type applied part has additional requirements for lower current requirements, like 50 microamps or lower. So these are review of the applied part that most of the medical customers are aware of. We're going to take a look at next is what is required. So we define some of the leakage current types. We define some of the type of products that have the applied parts on them. Now let's take a look at what standards would call a measuring device. Now, a measuring device is a leakage current measurement impedance network, now commonly known as an MD. So if you look at one of the images or one of the standards, and if you run across the word MD in a box or MD across the sentence, they're referring to a measuring device. Why they use measuring device is to kind of simulate a human body resistance to electricity. So the network was created to kind of simulate what a human body will look like to electricity, and this network is used to measure the resulting leakage current through a product or a product that's under test. Now, the body impedance network is a network of resistors and capacitor. They use this to kind of create a frequency response curve on the voltage meter. They do realize there's a frequency up to 1,000 hertz that could be hazardous to a human body. They want to make sure all parts of the frequency is measured. So they'll create a resistor and capacitor network in such a way that the voltmeter is able to measure the frequency up to 1,000 hertz. Then we go into fault conditions. So we have our network that we want to measure. We have the product that the leakage current is going to come from. Now we want to be able to simulate some conditions. So what are these conditions? In a normal condition, when you have a normal condition, when line neutrals are wired properly, you have a proper ground, the electrician has ensured that ground is properly installed. You're going to run into conditions when you have a condition that's called normal condition, and now you're measuring leakage current to the chassis of the product. Are you having any kind of excessive leakage onto the chassis of the product while the conditions are normal? Are there any leakage current to the applied part when there's a normal operating condition? Then we move on to single fault condition, measurement taken under single fault condition to simulate some kind of worst case scenario. What happens if the electrician at the hospital forgets to ground the outlet? If your product gets plugged into this ungrounded outlet, now is there additional risk associated with your product in shocking somebody? This could also mean that somebody broken off the ground pin. If an operator, a nurse, or somebody breaking off the ground pin creates additional hazard for your product to get shock somebody. Now, there's also conditions called reverse polarity, which allows measuring of leakage current if the line neutral were reversed. There's a possibility that the wiring or either the plugging in of the product is done in the wrong fashion. This will create a reverse polarity condition where line neutral are reversed. Does this allow additional leakage current? Now, these are some of the cases where the standard is trying to simulate conditions that could be seen in the real world. And they're trying to mitigate the risk for electrical shock to either the patient or the operator. The main question that you want to ask is, what is the severity of electrical shock or electrical current someone would be exposed to if they were to touch the device under test or your product that you're testing under such conditions? So what would happen to one of your products? Let's say you make 10,000 products a year. One of those products that went out in the field was hooked up to an ungrounded outlet. Now, are you ensuring that the leakage current felt by the person coming in contact with it, does that exceed 5 milliamps, 10 milliamps? These are some of the levels that people start feeling strong reaction to electrical current. How do we do this in our equipment? So majority of the manufacturer of this test equipment, they have what we call built-in networks. For our products, we use measurement devices that are built in. There's a few measurement devices are listed. There's a 60601 standard. There's a UL 1563. You could also take a look at the IT equipment. So these are built-in resistor networks that are required by these particular standards to run leakage current tests. Without having these resistor networks in place, if you're measuring leakage current, you're just measuring leakage current across a dead short or a shunt, and you're not getting. You may get a higher amount of leakage current compared to going through a network. Now, MDs do vary, so please consult with the appropriate standards that you're trying to conform to select an appropriate measuring device according to the standards you're trying to conform to. The standards that we're going to look at in the future slides right now would be the 60601-1, the medical equipment standard, medical device. So as I mentioned earlier, the network itself is inside our product. This is a resistor capacitor network within our product. Now, to run a leakage current test, you have to be able to power up the device under test, so also known as DUT. The DUT needs to be powered up at 110% of the normal input voltage that is listed on the label. So if you make products that are listing anywhere from 100 to 230 or 240 volts, you need to be able to test this product at 240 volts plus a 10% more voltage to consider over voltage condition. This puts you at a testing voltage at 264. This is the reason why you're not able to test leakage current tests using a normal wall outlet. You're not going to be able to generate 264 volts from a normal wall outlet. So you need to have a mechanism of either an additional AC source built in, internal or external, to power up this device under test. So let's take a look at device under test here. Give me 1 second. So inside this unit, some of the equipment does come with internal power supply that could output 264 volts. 260 volts are going to be outputted at line and neutral, and that would be enough to power up your product according to the standards. Now, you're overpowering the device under test to see if additional leakage could be seen compared to normal 240 volts. There's additional points that are taken into consideration where if you're running some additional tests, you may or may not be required to have probe high and probe low attached to one of your products. So as you will see later that when I go through the MedTest app note, depending on what kind of applied part you have, depending on if you're just doing a simple earth leakage, you may not be required to have this probe high, probe low setup on your product. So in device internally or externally using power supply will power up your product. What we're trying to measure is what would happen if your product is running in a normal condition, powered on full operating temperature, operating condition, while it's doing all these measurements. How much leakage can you feel on the chassis of your product? Now, generally speaking, if you have a well-grounded product, all that current that flows on the top of your product is going to go through the ground pin straight back to ground. So when you have a closed ground condition, you should not have any leakage current flowing on the chassis. The reason for that is you have a really good connection to ground, and all that current is flowing straight to ground via the low impedance path created by your ground circuit. Now, as you on the next few slides, we'll take a look at what would happen on a single fault condition. So here is a DUT, device under test, simulating plugged into our adapter box here, and everything to the left of the product here happens inside of unit. Now, these switches are mentioned S1, S2, S3. These relate back to the standards where you're required to do an open ground condition, breaking off the ground plane or ungrounded outlets. If you were to open up the S3 switch, how much leakage current can you feel or measure on the chassis of your product? If you were to reverse the polarity, so in this case, S2 is a polarity reversal switch. Line neutral are swapped to neutral and line. Your product is receiving, at the neutral point is receiving line voltage, and at the line voltage is receiving the neutral of the source. Now, does this create additional leakage? And then you have a condition called open neutral. This open neutral is counterintuitive. You would think that your product is powering, there's no power going into your product, you're expecting no leakage. But in reality, the line voltage does go to your product just because there's no return path back to your neutral since the S1 switch is open, but the voltage is still being seen by every component in your product. So your device might look like it's off. An operator or a patient might think a device that's off doesn't pose an electrical shock hazard, but in reality, there may be voltage coming into the product. It's just that does not have a complete path flowing back to neutral. It looks the device would be off, but there's still additional hazard associated with having line coming into the product. So we're simulating a condition where, what if the neutral wire opens up? Does your device cause additional leakage through this measuring device? So what happens in a normal condition? Let's take a look at a normal condition. In a normal condition, you have a device under test, or your product that you're going to be plugging into the wall outlet. It's going to have voltage flowing, or the current is going to flow from line side back to neutral side, powering up the device under test. Now, like I mentioned earlier, if there was any excessive leakage current flowing on the chassis of this product, you have a connection called ground. Now, this ground is there for any kind of fault current that may happen if there's an internal short. Additionally, it also takes any excessive leakage current to ground. So if there's any leakage current that's flowing on the chassis of the product, the ground is there to take this back to the neutral of the supply. This creates a flow of current, not just through your product, but through the insulation to ground. Having this ground in place kind of shorts out the measuring device, and you're expecting no leakage current through the measuring device while this switch is on or in place. So in real life situation, if you have a grounded product and if you kind of go and touch the product, you're not expecting to get shocked. The reason for that is that the ground, the chassis itself is grounded, and electricity is always going to take the lowest impedance or lowest path to ground. And the resistance of the ground circuit is usually in the 100 or 200 milliohms range. The electricity sees a human body as 1,000 ohms of resistance. So you have a order of magnitude 100 times higher than what the resistance to ground is. So it's always going to take this path to ground. Now let's take a look at what would happen in a single fault condition. We're creating a condition called open neutral. Again, even though the neutral is open, the ground is still taking care of any excessive leakage current that may be seen by the product. So with having open neutral condition, again, this is a single fault condition. A neutral were to open up, your device does not power on, but does that leak any additional leakage current to earth? Reverse polarity, another single fault condition called reverse polarity. Again, switch neutral is closed back up again. You have a condition where polarity of line goes down to neutral of your product, and then the neutral goes to the line of your product. How does your product react when you have a reverse condition called reverse polarity? Is there additional leakage seen by the measuring device? And now we get to an open ground condition. Like I mentioned earlier, if you do plug your product into an ungrounded outlet, if the electrician forgets to ground the electrical outlet box or electrical outlet, you may see leakage current now that could be felt by a person coming in contact with the chassis of your product. You're expecting the chassis to be grounded. The chassis is not grounded for one of the various reasons that I mentioned earlier. Now, how much leakage current can a person feel if they come in contact with a chassis of your product and if they're in contact with the low side of your power supply? Now, for wall outlet, the neutral is grounded to earth. So if you're standing on earth and if you're coming in contact with one of these devices under test or devices that are out in the field, you could expect leakage current flowing through you. Standard does allow some of this variation of how much leakage current that could be seen in a single fault condition. So this is an open ground, consider a single fault condition. You could have leakage current flowing when the ground is open. So the highest amount of leakage current you could see in a product or during a leakage current test is always when the ground is open. So if the ground was closed, obviously all the current flowing to the chassis is taken care of by the switch or the ground of your product. So just so I make sure everybody's paying attention, I want to kind of put up a poll question. I'll have Amanda put up this poll question really quick.
Hi, Vishon, the results are in. So which one of the following would create maximum amount of leakage through the MD? 30% said ground closed, neutral open, and reverse off. Nobody replied to the second. 60% said ground open, neutral close, and reverse off, and 10% said ground close, neutral open, and reverse on.
Thanks very much. So thanks everybody for participating. So the correct answer is C, right? So ground open would create the maximum amount of leakage current flowing through a person coming in contact with your product. Imagine all those other conditions. Doesn't matter if the neutral is open, reverse off, or on, as long as the ground is connected, meaning your product is properly grounded, all that excessive leakage current will flow straight to ground, not affecting anything on the chassis of the product. So a measuring device connected during a closed ground situation will most likely result in negligible leakage current. And open ground creates the highest amount of leakage current. Now this is true for earth leakage. When you go into some other types of tests like auxiliary leakage, you may or may not see the similar results, because when you go to the patient leakage itself is not dependent on if the ground is open or closed. You may see the same amount of leakage current depending on the condition you see here. So thanks for everybody for taking your time and participating in this poll question. Let's move on to the next part of the webinar here. So we're going to take a look at the standard itself. So all these things that I mentioned earlier, measuring device, leakage current test, having the product to be at 110%. Where does all this information come from? The standard itself is 60601-1 medical equipment standard. This allows, or this dictates what kind of products that needs to be tested under this standard. This also allows you to kind of go in and figure out if you have a B type applied part, if you have a F type applied part, do you have additional requirements for the F type products? Taking a look at 8.7 leakage current and patient auxiliary leakage current, the requirements that are listed require you to test in single fault and normal conditions. So you have a normal condition where line, neutral are proper with a closed ground. How much leakage are you going to see? So this is your normal condition, and a single fault condition. So again, if you have a single fault of open ground, a single fault of open neutral, a single fault of reverse polarity, what kind of leakage current are you going to see? It requires you to run the product at 110% of the highest rated mains voltage. Again, if you have a product that's going to be only sold in US, you cannot assume that it won't be transferred or sold to somebody in Europe that has 240 volts. So if your input label requires that the product could be used at 100 volts to 240 volts, so use the highest number listed on your input label, multiply that by 110%, or use 110% of that number to come up with the test voltage. So this is a product, you want to run your product at this voltage to see what kind of leakage current the resulting leakage current. Also tested at the highest rated supply frequency. So if you have products that are used at different frequency other than 50 or 60 hertz, please use the highest frequency that's allowed. So you want to be able to power up your product at the highest rated frequency and the highest rated voltage listed. Now let's take a look at some of the passing criteria. What is earth leakage pass criteria? You want to have a normal condition where leakage felt by the MD is less than 5 milliamps. So in an earth leakage test, even though you're doing open, neutral, reverse polarity, any kind of conditions, but during a normal condition, when the product is plugged in properly, the leakage through the MD should not be more than 5 milliamp. Now, if your equipment is designed properly, if everything is functioning properly, the earth leakage would most likely be less than 5 milliamp. Now, when you go to single fault condition, you want to also make sure the allowable limit for now is up to 10 milliamps, leaking to an applied part, leaking to a metal enclosure point. The 10 milliamp it is an additional leakage current allowance at those points. Now, during touch current point, for touch current, which is to a point where you're testing to an applied part, touch current, or a chassis that's not grounded, the current actually, the limits for the currents go down. So 100 microamp could be the limit of current as measured at that point. For a single fault condition, it could be as much as 500 microamps. I do have a copy of the table 3 chart on the next slide, which will review for some of the requirements that are listed for having AC leakage, DC leakage, having composite leakage. Just going through some of the verbiage in the standard itself. For clause 8.7.4 leakage current measurements, they do specify different types of leakage current. So as I mentioned earlier, if you're required to do what's called earth leakage current, take a look at figure 13 in this standard. If you're required to do touch current test, enclosure leakage, figure 14, and then following section, they'll tell you how to perform the touch current test for your product. Now, patient leakage general, this is where you have applied part. If your product does not have anything that comes in contact with the patient, the first 2 tests may be enough to qualify your product. But if you have applied part that come in contact with the patient, you have additional requirements that are listed in patient leakage section of the standard. Now, under this clause, there's additional requirement for patient lead to earth. This is figure 15 in the standard. Mains on applied parts. So if you have an F-type patient lead, which is really isolated from any kind of internal mechanism of your medical equipment, you are required to do what's called mains on applied part test, figure 16. There's additional requirement for signal input and output. If you have equipment that has signal input output ports on a medical equipment that could be energized, you are required to have an additional test called mains on applied or mains on signal input output, figure 14 and figure 17. So this says figure 17, but it could also apply to figure 14. And some other ones called mains or non-protectorly earth chassis points. So imagine having a metal point on your product that's not grounded, but it could be capacitive coupled and get energized and create some additional leakage to earth. If you apply voltage to this point, can additional leakage be felt by a patient that's connected to one of your applied part? And then you have figure 19 here on the left that shows you information about patient auxiliary. So now we're talking not about just the product to earth anymore. Now we're talking about between products. So again, electricity likes to take a path between two separate voltages. If you have 5 volts one place, 25 volts somewhere else, you're creating a voltage drop. So electricity or current itself is going to try to flow between those 2 points. Now, in a medical situation or a hospital environment, there's a possibility that a patient is connected to 2 separate applied parts. Now, does your product have leakage current between those 2 points? So this is where patient auxiliary leakage current comes into play. Not only that one of the applied part is leaking current, is there a leakage between 2 points on your product? So this is well isolated within your product, but what about the current between one applied part to other applied part? If you measure this and if it's above the particular allowable limit, this would actually fail the leakage current test. As I mentioned earlier, Table 3 is allowable values for patient leakage current and patient auxiliary current under normal condition and single fault condition. All these currents are listed in microamps. So if you take a look at the first one, the patient auxiliary current. Now this is, again, measuring between one applied part to another applied part. What kind of leakage current are you seeing? This allows for a DC equivalent if you have product there running under DC. Or you could have a AC and DC compiled into a AC leakage current. So some of the test and measuring equipment out there, including our Omnia series, is able to differentiate between AC and DC current. So you could filter out just the AC port, filter out just the DC part, or leave it as a composite AC plus DC. Again, type B applied part, type BF applied part, and if you had another type CF, which is the more stringent one, you could see how the leakage current requirements are down into 10 microamp range for AC and DC, and a single fault condition down into 50 microamps. We're trying to measure 50 microamps of leakage current being felt or delivered or that may show up on an applied part. So patient leakage, again, this is where one of your applied part is leaking to ground from patient connection to earth. This is exactly what the description says. If you're a product connected to a patient, is it sensing something for your product to measure the heart rate or some type of other functionality? Now, at that point, does it allow additional leakage to earth through the human body? So allowable limits are listed here, going across for AC and DC separately. Now the measuring circuit, these are all the measuring circuit listed in these figures, and we'll review a few of them in the next few slides. There's additional requirements for external voltage on SIP-SOP. So this is, again, when I mentioned, if you had a patient leakage current, are there additional leakage current felt by this applied part if in case somehow the input port gets energized? What if the IT department was running some tests, somehow they connected their the cable, the LAN cable, into an outlet or some kind of 100 volts outlet, and that voltage is now seen by the product that's connected to the network? Does that cause additional leakage to your applied part? And normally the design of the medical equipment does not allow, it is really well isolated, shouldn't allow any kind of voltage felt at the signal input to be affected by the applied part. But this is what you're trying to measure during either design phase and also during production type testing. And then down here, you have total patient leakage. So there's also requirements of having same type of applied part. You could have 4 of the applied parts doing the same thing. It allows you to tie those 4 points together, and having additional requirements allows you to have different leakage requirements for the same applied part. So again, multiple applied part and how you would treat them under Table 3 of the standard. Table 4 is a little bit more generic for earth leakage. As you could see, we mentioned earth leakage is the current that's being felt on the chassis of your product for equipment connected to an ungrounded outlet. And then you have some of the enclosure leakage, a metal conductive part on the product, and what kind of resulting leakage current can be seen. Now these are listed in milliamps, so that's also, you also want to be careful with the numbers listed. The measurements are usually done in microamps, and if the milliamps are listed, you may want to adjust for those. So let's take a look at one of the images mentioned earlier. So in standard 60601-1, figure 14, this is kind of showing you how to run a leakage current test. Again, we mentioned that the product needs to power on, and the standards is telling you to use your mains input using a transformer, an isolated transformer, to get not just the safety section. You want to use an isolated transformer to keep your operator safe, also to get some good and accurate measurements if you had an isolated power supply. Applying line voltage, line neutral here. The switches I mentioned earlier, they don't correspond to the figures that we used earlier, but these are all listed in the standard. S1 has its own definition, S5 has its own definition, so does the rest of these switches. Now, just taking a look at this, you could see that a measuring device could be between enclosure point, which is, this is your DUT or device under test, and these are the line and neutral inputs of your product. This could be applied part, any applied part. So the dotted line means an optional test. For this figure itself, if you had any applied parts, you could tie it back down to the neutral side. But again, the placement of the MD is important, and where this MD falls in is what the test definition is. For this one, it's an enclosure leakage. The reason for that is that it's coming in contact with an enclosure point along the product or the chassis, going back to the neutral side. So imagine having a human being, the measuring device, the right hand touching the product, the left hand or the feet touching the neutral side. Now what you created is that in a situation where the protective earth, PE, is opened up, S7, if the switch S7 ever opens up, the resulting leakage current that happens due to the factor where the electrons go in every direction all the way to the chassis, and normally they would like to go back using the earth wire, which is low impedance path to ground. But since S7 is open, it's going to look for a path, alternate path. So what does it do now? All this leakage current that's happening through the insulation finds a path through the measuring device or a patient equivalent, and it goes back to the neutral side. So what we're measuring is leakage, line voltage coming into your product, going back to neutral side to power up your product, but any excessive leakage that goes to the insulation that's being caught on the chassis with an open ground, it can't flow this way because S7 is open. It's going to flow through a measuring device that's in place. Now, if this leakage current is more than 5 milliamps, 10 milliamps, your product does not qualify under the standard. The reason for that is at particular voltage, at a particular current more than 10 milliamps, there's a possibility that the person can't let go anymore. The muscles react to current higher than 0.5 milliamp. At 5 milliamp is kind of like shock hazard, and at 10 milliamp it's possible that the muscle starts contracting and inability to let go anymore. So having small amount of leakage current on the chassis allows a dangerous condition of shock hazard. Let's take a look at one other figure. So this is when we mentioned auxiliary leakage for patient connection. So again, where does the MD fall in is important. You have a normal line, neutral, powering up your product under device under test. Any excessive leakage, so you have applied parts. These section mentioned 4. These are any applied part that are functioning as an applied part. Is there any resulting leakage current due to this application of voltage that's powering up your device? Is there any leakage current that's being felt by the applied part? Again, this is one of the scenarios where having open ground or closed ground doesn't really affect the leakage current that's being seen by the applied part. All the leakage that's going to happen is due to the nature of how isolated the input is to the output of the applied part. The biggest isolation you get for a medical device, if you're using a AC to DC converter, comes from the power supply. So depending on what kind of power supply you buy, either really isolates your outputs, which are applied parts, SIP-SOP connections, any chassis points, or buying mediocre power supplies would create issues for you passing this auxiliary or patient leakage test due to the nature of a leaky power supply to ground will create flow towards the applied part and back through the measuring device to the neutral side. Again, this box here is within our product. We are giving the test equipment a point to measure to, which is called a probe high point, and then the other side of the measuring device is internally referenced to the low side of the transformer, and we're measuring any leakage current that flows through the insulation to applied part back to the MD. And if this MD ever records more than 50 microamps, 100 microamps, 500 microamps, 5,000 microamps, whatever the limits are that we saw earlier, you do not does not successfully meet the requirements of the standard. Having said that, I want to take a look at one of the app notes that was created to kind of address how the test works and how that could be used using our equipment. I'll have Amanda use the chat box to put a link to the app note that we have created. And when you open the app node, this is what it looks like. It'll say IEC UL 60601-1 3rd edition Med Test application node. And a Med Test is a system that we create using the equipment that AR or Associated Research manufacturers to create a test system for you to do your leakage current test, your mains and applied part test, even SIP-SOP connection if you had to. And the reason we do in a particular fashion is that you don't want to depend on the operator to do all the switching for you. There's a lot of wires that need to be changed around. And if you are able to run this in an automated fashion, you're not depending on the operator to perform the critical task of having the connections in the right place. So let's take a look at the app node itself. So quickly review what's needed. An electrical safety compliance analyzer, 8200 series is our Omnia 2 series. Some of the scanning matrices. This is what makes possible for us to reroute or route connection points from an applied part to an enclosure point to an earth ground to be able to run the leakage current test. We also use some scanning matrices to do multi-point ground bond tests. So if you are ever required to run ground bond tests on more than one point, a scanner with 8-point ground bond channels could be used to create a multi-point ground bond test. So let's take a look at this. These are the equipment and their capabilities. And we're going to start with a normal ground bond test and what is required to run a ground bond test. I'm going to skip over the safety test. This is well covered in our previous webinar, and if anybody's ever missed those webinars from this year, you could always find them in our archive section. We cover ground bond tests, we cover the HiPod test. This just shows you how these tests could be ran. Since the webinar today is about leakage current test, I want to skip over straight to the leakage current test for from this app node. So this what brings us to earth leakage. If you take a look at the clause 8.7, leakage current and patient auxiliary leakage, you could take a look at how a test setup like this allows your DUT, which is device under test, having two applied part 1, applied part 2, to be able to run in a fully automated fashion. And I mentioned earlier that you're required to have a source that will power up the product at 110% of the voltage. We have a capability of having internal power supply that will provide 264 volts, up to 270 or 280 volts can be provided to your product. And then we're doing the resulting measurement internal to our equipment. You will also see some of the conditions here. Let me see if I can zoom in. So there's probe high, probe low. These are connection points. So we want to, if in case we want to show this test equipment where the connection point is, we're using probe high, and the probe high could be connected to multiple points on your device in the test. So it could switch between front of the unit, back of the unit, side of the unit, any which way you have probing points on your product. So this is earth leakage. Again, we're using internal power supply to power up your product. Internally, we're going to open up the ground, measure any resulting leakage flowing from line side through the insulation of the product. Again, let me bring out the spotlight here. Any normal current will flow from line back down to neutral. This will turn on your device or run your device normally. And then if any leakage current happens towards the applied part, any leakage current that happens towards the chassis or the ground is flowing through the insulation of your product, is going to be caught by the measuring device that's inside the unit according to the standard. Take a look at the next section on here. Is having an enclosure leakage. So again, enclosure leakage, the red kind of shows you what's active. If an enclosure leakage is measuring between an applied part, you're activating those 2 points. Again, measurements done onto those 2 points. We're measuring between probe high and probe low, or it could be probe high to line. But these are all configuration. Once you have an idea of what current you're required to run or what test you're required to run, we could always help set up a scenario where all the switching is done automatically. And then we have an applied part leakage, followed up by a mains and applied part. So I wanted to review this really quick. I know we get a bunch of questions on mains and applied part testing. It is one of the most rigorous testing out there. You're actually applying line voltage, and that's why you see a secondary power supply. The standard actually requires you to have a T2, which is a transformer 2 in the standards, that will say what would happen if line voltage from a secondary source ever made it onto your applied part. What is the resulting leakage current seen by the device in the test? Now, to explain this in a visual sense, you want to take a look at, if you're in a hospital environment, if there's a secondary source on a different side of the wall than what you're connected to. So if you're connected to a medical equipment, and then something falls on you, something energizes you to 110 volts or 260 volts. What happens if you are connected to this medical device when you get fully energized at line voltage? Now, this voltage that just fell on me may kill me because it's an accident. But does that allow your product to leak more current or provide a path for this voltage back down to ground? But because if your product provides path to ground, it would actually create shock hazard or more severe effects on the human body that's connected to it. So you're simulating voltage falling onto your applied part through an MD and any resulting path that it may create through your product. Now, there's tests previous to this that kind of ensure that this doesn't happen, but this is just like a verification on it. So initially you run a high path test, and we covered the high path test in previous webinars. If you run a high path test, you're ensuring isolation between mains input, line neutral to ground. And then also you run a high path test on an applied part, which means you're isolating the applied part from the mains input or the ground. So there's enough isolation there during high path tests. But now what happens during a normal run test, like if you're actually powering up your product? Does additional relays get engaged? There's additional path of current created because the device actually powers up now. And that's one of the things that we see a lot when we do consulting work, that the idea that having the product turned on fully functional as required is not being utilized properly. So you can't just do a quick test of, oh, the unit turned on. If you have attachments, if you need motors to come on, all those things need to come on. A full operating condition that needs to be achieved for you to really see the leakage current that you see on an applied part. If you have software in there that takes 30 seconds to boot up, you need to allow 30 seconds for the unit to properly boot up. Energize all the relays it needs to, and you want to create, you want to not meet the requirements for minimum standards, you want to achieve the highest standard. So allow the unit to go to a full operational mode, allow it to leak the highest it can, and then measure the leakage current. Now, are you seeing additional leakage? Are you seeing more than what the standard recommends? This could be also internal. I mean, most of the companies have internal documentation or internal compliance people available to answer these questions for you, or create documentation to kind of see what is acceptable risk, what risk can they mitigate by not running these tests. And while the standard does not require you to run most of these leakage current tests during production, if you have a medical company, or if you're producing medical equipment, you want to be ensured that during production nothing went wrong to that applied part. During your prototype phase or design phase, you have a good isolation between the line neutral and this applied part. But what about in production? What happens if the transformer that's used to connect these 2 points somehow comes in contact with applied part? And then if you're making tens of thousands of these products, it only takes one product to be bad to cause a big headache for companies that don't run these tests during production. So not only that we have seen that these are ran during production, we recommend leakage current to be ran during production to make sure every product that's being shipped, at least the average is done to kind of mitigate the risk of leakage current test failures for your product. Again, so this is mains and applied part test. You may or may not be running this right now, but if you were to require to run these, or if you have any questions on mains and applied part test, we're always here to answer those questions for you. And I'll have Amanda. Amanda's already posted the link to the app note. If you have any questions after reading the app note, do consult with us and contact us. I also want to point out that we also have a big guide to electrical safety. So let me see if I could pull this up here to the first page. So the safety, this is another guide to electrical safety testing. This goes over a bunch of different requirements, classification of class 1, class 2 products, why the testing is done, nationally recognized testing laboratories, some of the definitions. We also want to take a look at visually how the tests are being performed. So if you just skip over all this information about high pot test, ground mount test, and again, we'll put a link to this in our chat box so you have access to this document. But I want to show you the section where visually what are you doing with the product when you're testing leakage current. So take a look at earth leakage. If somehow a medical device is ungrounded, a measuring device is MD, comes in contact, how much leakage are you going to see flow from the mains input back through this person back to ground? That's entirely possible. We've seen numbers like 2 milliamps, 0.5 milliamps. So 2.5 milliamps could happen through an MD if the ground is opened up. That's enough to feel the shock. Like 2.5 milliamps is enough to feel the shock if it was ungrounded. It's still within the limits of the standards, but you want to ensure that an ungrounded product does not cause more than 5 milliamps of leakage, 10 milliamps of leakage, or 20, 30, or 40 milliamps of leakage, which could be hazardous or even possible death scenario at that point, where more than 20 milliamp could be fatal. If you look at enclosure leakage current test, enclosure could be any point on your product that's metal accessible that could be energized. If I'm touching that product while your product is malfunctioning, am I going to feel leakage current through the measuring device? So we're measuring this leakage current flow from the mains input. Normally it stays within here. There's a fault that happened, let's say reverse polarity. Somebody switched the polarity on the input. Now, is there additional leakage flowing through me because the polarity was reversed at the input? This could be considered as point-to-point or patient leakage, right? So if you connect it to 2 points onto a medical device, an applied part 1 and applied part 2, now not only do you have to worry about everything flowing to ground, now you have to worry about a flow of current between applied part 1 back to the product applied part 2. So is there any internal leakage flow? Because again, the current here could be also shock hazard, appropriate for shock hazard. So you want to be careful of performing all the tests that apply to your product. So going back to the slides, real quick review or taking a look at patient auxiliary tests. The last image that I showed kind of shows you the information on what an MD or where does an MD fall in. So if I'm running my product line neutral normally, how much current is this person going to feel if they're in contact with both of my applied part, if I have two applied part. Applied part 1, back down to applied part 2. This is known as a patient auxiliary leakage current test. The device needs to be powered on, 110% of the voltage. How much leakage can the person touching those two applied part feel due to the line input of the product? The scenarios again are similar to switch 7, 10, and 1 or S5. You're actually simulating different kind of switch condition or single fault conditions. Mentioned earlier, mains on applied part test. This is the definition. This is the actual figure in the standard, which shows you how to perform a mains on applied part test. Again, mains voltage from a secondary source, T2, it needs to be isolated again. T2 needs to be an isolated source for operator safety during production run or safety test. And also, they show you to simulate a resistor for current limiting resistor. Again, an MD coming in contact with a secondary voltage source. Somebody sleeping in the bed at the hospital, lamp falls on them, and they get fully energized at 260 volts or 240 volts. And then if that voltage ever makes it to your applied part, does your applied part allow a flow back to the neutral side? And if there is this flow of current, then what happens to the MD is that MD is going to feel all that current. So we want to make sure these 2 points, which are known as applied part, doesn't allow even line voltage to make it through the insulation back to the neutral side. So that's where the protection is, right? You want to isolate your outputs from your inputs, and you want to keep it as floating or as isolated as possible. And the different types of requirements are based on the applied part you have. If you have a B-type applied part, your requirements are not too much. If you have an F-type requirement, these are additional isolation, and you have to be able to prove that this additional isolation exists, and not only during prototyping phases, but also during production. Are you checking this during your production? Is the isolation that was designed to be there? Is it still there when the unit is being produced? Taking a look at so again, yeah, so this is the mains on applied part section. You want to make sure that applied parts are isolated, not only for high pot test, but also during application of mains voltage. Okay. Additional test and consideration, mains on applied part is figure 16, signal, external voltage on signal input output, figure 17, and then external voltage on metal accessible part not protectively earthed, figure 18. So these are additional figure may or may not apply to you, but there are in the standards to allow you to run a proper leakage current test. So having said all that, I want to put up a poll question about how confident you are about leakage current test itself and being performed properly according to these standards. Now, I'll give you a few minutes to answer this and have Amanda put up a poll question.
Hi, Bashan. The results are in. So how confident are you that leakage current tests are being performed properly according to the standards? 0% reply to highly confident, 67% reply to confident, no majority of requirements and how they apply, 17% reply to somewhat confident, know only a few aspects of the LCT, and 17% replied to none, having a hard time determining test points and configurations.
All right, thanks, Amanda, and thanks everyone for submitting this poll questions. And this is no different than what we have seen in the journal customer base that we have. We have customers that have some standards, or somebody wrote the standards, is no longer with the company, and they're referring back to points and on the test equipment or points in the standards, but they have no reference guide to it. So we want to be able to help you with this. If you're using our equipment, if you're using somebody else's equipment, and want to move over to using AR equipment, we will more than likely want to be able to guide you into being highly confident about performing the test properly. So if you have questions, if you have any additional or detailed questions, we would definitely take a look at the setup that you have, answer any questions you may have. We do offer consulting services. This is a consulting services that we started, and I've been on a few consulting trips myself, taking a look at what every other manufacturer is doing, what their pitfalls are, making some recommendations on how to properly test, and if they're not performing tests according to the standards, kind of align them back into performing the test properly. So we do help with some of the education section also for safety around the high voltage equipment, or general safety during leakage current testing, and also kind of try to automate systems where you're moving away from an operator making all the connection to go in a fully automated system or semi-automated system where you're less and less dependent on or making operators making errors, and making sure your product fully complies with the standards. So this information can be available on our website. You could take a look at iconixusa.com consulting, or reach out to our department here, applications at Iconix USA. Having said that, there's additional resources available on our website under education support and educational resources. This is our final webinar for this year, and I thank everyone that attended previously, also everybody that attended today. We will be posting our schedule for next year come first of the year, so sometime around 1st January or February, we'll be posting the schedule for the rest of the year. We may decide to change it up a little bit to get more content, more fresh content in for next year, and try to figure out what really is helpful to our customer and provide that information. So I could open up the floor right now for any other questions that anybody may have or like me to answer. Okay, so it doesn't look like there's any questions, or maybe Syed's gonna.
Yeah, Bashan, there's no questions. There were a few on the chat line which I answered, so nothing else for us to discuss.
Okay, all right. Well, I'd like to thank everyone that attended, and again, thanks for joining us. Stay tuned for next year's webinar list coming up in January. And if you do have questions, if you're using our equipment, we would like to get you more confident about leakage current testing. Always reach out. You could use the address here, amanda.booth@Iconix USA, and she could put you in touch with one of our application engineers or the consulting department. Thanks everyone for attending.